Today we have Chris Gale, head of geospatial analysis capability at the Office for National Statistics, who is going to talk to us about data-driven small area geographies using nested grids. Chris, the floor is yours.
Thank you very much, and good afternoon, everyone. It's a pleasure to be here to talk to you today. Hopefully, you'll find the next 40 minutes or so interesting. And if you have any questions, I'll be more than happy to either answer them now if I can, or take them away and maybe answer them at a later point. So I will just first of all just like to say that while I'm here presenting this to you today, this is actually the culmination, and not even a culmination, it's the continuation of quite a lot of work by a few different individuals. And I've sort of name check them now. So I have just big thank you to David Keir, Heather Porter, Rob Coletta, and Musa Cherikini for working so hard on this over the last few years. It's been a labour of love to get to where we are now. And it's an absolute pleasure, as I say, to be here to sort of talk to you through what we've done and what our thinking behind it is, and also hear any thoughts about how things could be improved or different approaches we can take, because this is not a finished piece of work. It's very much a work in progress still, but also something where we are still thinking about some of the methodological implications of it as we move into the future of small area statistics for England and Wales. There we go. Okay, so this talk will be a brief overview of the talk here. So I'm just going to give a bit of background just so people are up to speed. I'm assuming quite a few people on the call will be aware of the small area geographies that we have in the UK, but I'll just give a quick refresher just to make sure everyone does. Give a little introduction to the hierarchical grids, nested grids. I kind of use that term interchangeably. I don't know if that's right or not, but that's what I do. Making the actual grid itself, some disclosure elements of it, the actual Python package that has been created, some comparisons, examples of what this output can do, and then some of the bits we're still working on. So, some background for everyone. So, in the UK, in England and Wales, we have output areas as the smallest area of reporting geography predominantly for the census. So these are reflecting the residential population, so nighttime, and they use building blocks to create the lower layer super output areas and the middle layer super output areas, LSWAs and MSWAs. Just in England and Wales, Scotland have also output areas, and Northern Ireland have just replaced their what were previously small areas with data zones. So these are how we have done small area statistics in the UK for the last 20 years, 30 years if you include Scotland in that as well. And they are very much built around disclosure. So they're trying to be a small areas where we don't want to basically people to be identified, which is why they have minimum threshold values to create the geography. So they're pre-canned. So we create them before data effectively gets attributed to them. So they're based on minimum people and households, and it does differ between the different countries what we do. So now in England and Wales, the minimum is 100 people and 40 households. In Scotland, it's been 50 people and 20 households, and in Northern Ireland, it's 40 households. So again, different ways of doing things, but they've been stable, and they've basically are marked much better than how things used to be when we had things like enumeration districts where they were designed around where people used to walk. They are designed for release of small area numbers, and they allow the release of much greater width number of statistics that would otherwise be possible using more older methods. So we are quite lucky in this country to have something as established and as relatively stable as well. In England and Wales, the output areas, most output areas have remained constant over the last 3 censuses now. So which was not previously possible. Scotland would be something similar. Northern Ireland slightly different because they've had to redraw their boundaries. But there are limitations with them. They're not perfect. They're not for every single use case, and sometimes they get shoehorned into using other types of data with them just because there's nothing else, there's no better alternative. So as I said, it's individual data aggregated to predefined geographies, and this is kind of the thing you'll get. So this is Southampton. If anyone's familiar with any kind of more rural or sparsely populated area, the output areas tend to be much bigger in size, but much bigger area, This is because they need to cover the whole of the country, and to meet that minimum criteria, they have to literally stretch out further and wider to cover that minimum number. So this means you kind of have the situation where in urban areas they're quite small, and in rural areas they're much bigger. So there's much variation in size, and that can be an issue when you're using other data sources, or you're trying to link data sources together using this output area data. So this is where the kind of idea of a grid comes from, like, because a grid is stable. At least in a human lifetime, it's stable. We are not moving that quickly, where a grid is not going to be, is going to suddenly shift its boundaries dramatically for the purposes of what we need it for. We're also not ordnance survey. We're not surveying. We don't matter if it's a few millimeters out. We do not mind. It's the general principle of a more static geography built around a grid has advantages. So the question then you might be asking is, what have ONS previously had in this space? So we haven't had, this is what we're talking about today is new for us, but we're not new to grids. At least we're not used to the Geostat 1 kilometer grid. So this is a Eurostat, so they're the European Stats and Data Agency, and they have something called the Geostat grid. So this was introduced just over 10 and a bit years ago. It was introduced prior to the last round of censuses in the 2010s. It uses the ETRS 89 coordinate system, reference system, which is, if you look at the map, it makes the UK look wonky if you would compare it to the British National Grid, or maybe you're looking at a map on the weather forecast. And it's had limited previous use. So we had to do something when we use this, when we were part of the EU. So we had a legal requirement to effectively just have a population count on our 1 kilometer resolution. And that was done using postcode counts, which we released it was one of the releases from 2011 census. So that was it. We basically just took a postcode count, which we then linked postcodes as a point to the grids, intersected them, did some aggregation, and that's what you see on the map in front of you, is that the output of that was it. That was pretty much our only requirement. Obviously, a 1 kilometer grid has some issues when it comes to urban areas. A 1 kilometer might sound small, but it's quite big when you're in the middle of a city center, and there's a lot of people living there, especially in places where there's high density housing. And you find that they're just too coarse. They don't give you the resolution you need, which is why when we're thinking of ideas, we didn't want to go down the idea of having just a 1 kilometer grid as a replacement for this, or at least, or even indeed an expansion of what we've done previously. So this is where the nested hierarchical grids concept we came up with, and this has been on the draw. We've been thinking about this since about 2018. It's not been a continuous piece of work we have done. It's something that we kind of had to sort of dip in and dip out of as other things have come and gone. Just the odd global pandemic gets in the way of these things, unfortunately. And we've just tried to make progress where we can, with a view on the 2021 census that we in England and Wales, which is, as you may have heard this week, we've had more releases with the customized data available. Tools are now available for people to use. And that was obviously allowing much more data to be accessed via more traditional geographies. Our hope is that what I'm presenting here today will ultimately be something we can maybe use to disseminate univariate statistics from the census at some point further down the line. You can ask me a question when that will be, and I can give you a very woolly, I don't know answer, but I will do my best. So why nested grids? So the idea is that we want to build a geography from the data. We don't like the idea of having a pre-canned geography. Obviously has some advantages, as I've alluded to, but it has some disadvantages. The idea that we have to spend a lot of time. So for reference, to update the 2021 output areas, it took 3 core people with lots of people who are helping them over a year to do that, because of the complexities and the availability of data. It takes a long time to update geographies. Now, obviously, that maybe could be optimized in the future as processes and work practices in terms of reproducible pipelines and things like that improve, but it still takes a big effort to improve, to update them and maintain. The idea of just having a code way of effectively taking a record level data and building a geography around them has some advantages. And the idea of why it's hierarchical, again, is to make it flexible and allow more granular outputs that may disclosure. So the idea then is that obviously in urban areas, if you can go below a 1 kilometer level where appropriate and still have not break any disclosure rules, then that is a positive thing that we should try and work out how to do. It also can have zero counts. We don't have to have that full continuous coverage of the country. Not everything has to have a value above a certain number. 0 is a perfectly acceptable number. And also it has other advantages. So it increases interoperability with other data. So environmental, I'll come on to that towards the end of the presentation. But also, as I allude, one eye on the future. We don't know what the future of the census is going to be at this point in time. At least I don't. If anyone else does, please let me know. And the idea that how small area geographies can be produced in the future, having a method like this is definitely a string on our bow in terms of something we don't have to develop. It's something we can just maybe modify or do something if the future is slightly different to how we will do small area geographies. So it's giving us some, as I said, more options for how we go about doing our work, and ultimately trying to disseminate small area statistics to people who want to do interesting and cool analysis with them. So what design did we pick? So we designed variable grid cell sizes of 1 kilometer, 500 meters, 250 meters, or 125 meters. That's where the nesting comes from. So 125 meters is the smallest cell this methodology can produce. It's obviously not the greatest size of a cell to have. It doesn't really fit with like 100 meters or 50 meters or 200, but obviously there's a logic to where we've gone here, and we determined the idea of having something that nests within 4 levels to be more beneficiary than having 100 meters, because that then can't really nest within anything it gets too big effectively for what we're trying to achieve. We designed it so a user-defined minimum population of thresholds could be applied. So the idea is not built around we're not hard coding in the idea that it has to have a minimum number of people. The idea is that it to be flexible. For those who code, that's not a groundbreaking thing to say, but in terms of actually how we approach this, in terms of giving us that flexibility, thinking about these things at the onset might sound obvious, but it actually means that we're not hamstrung or find it challenging to make any changes in the future, depending on if we have changes of requirements, or we find that this is widely adopted for the use as intended. And one of the things I'll come on to, it'll make more sense probably as I talk through it, is designed for analysis, which sounds like a very obvious thing to say, but we're not necessarily thinking this as we don't want numbers to, like, the real world boundaries are not square. We don't live in the country where we have straight lines for boundaries. We have jaunty angles. We have a lot of history to deal with where our boundaries are and why they are the way they are. And obviously a grid with very straight lines and the 90-degree angles doesn't necessarily correspond to that. So that means if you wanted to get a total for a particular place using this system versus, say, the local authority or some administrative geography, the numbers might not match. Now the question is, does that matter? And that's one you might can ponder in terms of as I go on. We have our views on this. We have got 2 trains of thought in terms of where we could go with the design of this, but it'd be interesting to hear if people have perspectives on this. Just because, again, we haven't really talked too much out to the general public about this. We've been to a few conferences and sort of talked a bit. We've never spent as long as 40 minutes talking through this methodology. So this is really the first time it's getting an airing. So again, any views be very welcome. But before I can actually talk about the producing the Python script that does this, I need to talk about the actual grid itself, because that is fundamental to how both the script works in terms of the logic, but also how we can actually go and do what we do. So hopefully most people are familiar with the British National Grid. What you may be less familiar with is the fact that it actually goes a very long way. You might be more familiar with the traditional 100 kilometer cells that cover Great Britain, but actually, if you were to go, it goes to A to Z without I. It covers all the way from to the west of Iceland to northern Italy. It does cover quite a long way. Clearly, it's not designed for going out to those extremes, but it was a part of our thinking because there's There's been quite a lot of interest in UK statistics, more so over the last few years, to do with things from government. I've been definitely more interested in it. And the British National Grid doesn't cover Northern Ireland officially. In practice, the bit that you would normally see covers all of Northern Ireland except for like 100 meters in a farm right in the far west. But because the British National Grid can extend beyond that, we have decided to use this. And so actually what our method is could use any of this. So if you wanted to apply this method using British National Grid to Belgium, you're more than welcome to, because it will work. The QR code on the right is me thanking Stack Overflow for all their help, for me asking really random questions and people putting up with them and coming up with solutions. So creating what you see on this map was all done in some R code. So if you ever wanted to create the British National Grid at a 500, 100, 10 and 1 kilometer level, scan that, run some R script, it'll do it pretty quickly for you. Yeah, so that was the first thing, is trying to get the actual grid and build one ourselves made the most sense. Then there's the sub 1 kilometer level. And again, thank you to Stack Overflow for basically doing this. And there's also the numbering system, which I'll come to on a later slide. But this effectively is, so the 1 kilometer, then broken up to the 500s, the 250 and the 125. And that creating that grid is important, because knowing where things are, again, important. But the actual thing that makes the key, and this might not be this probably is one of my more drier slides, the coding element of it. Now, that might not sound a particularly enthralling thing, but actually it's quite important, because it's how the code knows where things are. It allows the code to operate in effectively a non-spatial way, which is important, because as anyone has dealt with spatial data versus tabular data, we know which one works quicker in a more code-based environment. So actually, anyone that's familiar with ONS geographies will be probably familiar with a 9-character code called a GSS code. GSS is Government Statistical Service, if you weren't aware. And that is made of the first 3 being an entity code, and then a unique 6 being the code for that particular area. So output area start E00 in England, for example. And we actually have a written policy that says the code shouldn't have any intelligence built into them. They should just be 9 characters, which is why obviously we've now created a 12-digit code with intelligence built into it. So what we have done is we've put an entity code that follows the rule that, so G is what we've gone for at the moment as a letter, not to be confirmed, but that's what we're playing with. And then we put the Ordnance Survey 1 kilometer cell reference in. So again, you know where it is, because it's a well-established coding system for coding geographies. And then 3 digits at the end. And why the 3 digits at the end are important, because that is where you can basically tell where you are based on those digits. So at 1 kilometer level, it'll just be 000. Then at a 500 meter level, it'll be 1 to 4 at the end. Then within the 250 of that 500 meter, it'll be 1 to 4 again. And then the 125 again will be 1 to 4. So there's actually quite a few permutations, but actually it means that you can have every single cell, it covers the whole of that previous Iceland to Northern Italy, can be covered in a 12-character code. It doesn't even if you just remove the ONS, it's obviously only then 9 characters down to 125 meter cells. And this is the logic itself. Again, it's all it is. So everything is repeating. It's saying, so when you're doing the actual algorithmic side of producing these outputs, you don't really need anything more than this, because you can tell where, you know that 222 is a 125 meter grid cell in the bottom right hand corner of a 1 kilometer cell. So you have some built-in intelligence, and that allows you to do the moving around a lot more simply. So actually, that's all you need. All you need is this grid system with this coding and some data at a record level. So UPRN is what we have data. So that's what was captured for the 2021 census. And then you can just write some pretty simple script, have a minimum number of people or household you want to have, and you can produce an output that looks like this. So hurrah, some simple R code has done this for us, and produces output. I should at this point say that all the maps you're going to see in this talk are all based on synthetic data. They're not real. So anything you might see or at a smaller level is not real things, that are not real data from the 2021 census. So anyway, we've done this. Great. Why has it taken us 4 or 5 years to get to where we are? It's because we've made it complicated. We've made it complicated for ourselves, and we've made it complicated for very good reasons. So one of the reasons, or multiple reasons why, record swapping. So as I will come on to in terms of how we have approached where these numbers are and how we've determined where we believe the threshold should be for this geography, it means that if you're one shy of hitting that number, then automatically your cell gets aggregated up to its parent cell. So if you were one person, if one cell had, say, 24 people and the neighboring cell had 26, because this one had 20 and the threshold was 25, what will then happen is they would all get aggregated up irrespective, even though that you could borrow one of the 26 to make them both 25 and it'll be fine. So record swapping is part of the methodology we've created, and it's to produce a more granular output because of it, to enable sort of a more granular output. It also has that inbuilt disclosure control, which introduced uncertainty, which my colleagues who are in charge of that, they like that element of it, because it means that while we do our best to kind of keep things where they should be, by the fact that you are producing outputs where this is built into the way that the algorithm is working, there's always going to be a little bit of uncertainty if the numbers you're seeing actually truly reflect where people are, which enables potentially smaller thresholds as a result. So we haven't actually agreed on a threshold for this. So I said about output areas having 100 people. It is possible that we could get a smaller threshold than an output area from this geography, which is something we'd be keen to do if we can. And I'll come on to again later on. I'll do some comparisons to show what is possible between the two methodologies, between this and the output areas. But that's really some of the key main points. So actually, that's fine, but what was our logic then? Because if you're going to have record swapping, you can't swap everything. So what did we decide? So effectively, at the top level, a cell is considered to be kind of it's got two states. It's either over or under. Makes sense, right? So the over ones are fine, as long as they stay over. The ones that are under are the interesting ones. I said previously that zeros could be fine. So when we say lower region, we're looking at numbers that are from between 1 and a defined number. So whatever we feel is appropriate, where we feel it's appropriate to lose those people from that cell and they can be moved elsewhere. You then got the opposite, which is the upper region, where they're so close to hitting that threshold that they will need to borrow people from elsewhere to make up that threshold. And then you've got that center region where we don't want to move people around because we're basically moving too many people around in those circumstances. We have to have some stability where records are, and we need to keep them where they are. So at that point, we don't touch those records. If any cell hits that range of numbers, it means that cell and all its neighboring cells get aggregated up to its parent cell, and then the same logic is then applied to see how far up it gets aggregated. And to give you some examples then of this, so so the yellow cells example A. So this is based on thresholds. So between population of 0 and 10 and households of 0 and 5 being the lower region. So if a cell hits that size, so example A, the bottom left-hand corner, those numbers are both below the threshold, and that means, and also there's a cell on the top right, that's the blue color, that's slightly below the threshold of 50 people and 25 households. So the way the algorithm would work is it would identify that the ones over the disclosure limit, I mean, they could take from them, but it shouldn't take those. It should try and prioritize taking from the lower region and moving them somewhere else, because that means then it can effectively be a zero count, which it is, as you can see, and then there's other cells, and then all above, and that allows you to have one blank cell and 3 cells all above the threshold. With example B, again, it's something similar, except the yellow cell gives away all its population to the blue cell, and then the green cells then donate some additional ones as well to make up. So it's the logical order it goes in. So it looks for the ones where it needs to take people out, and then if it still hasn't made it, it then looks to see if it can take anyone from anywhere else that are over threshold, and then produce an output. And then the last one, example C, modifying the red cell, so the red cell fits in that center range, would introduce too much change, which means that all those 4 cells then get aggregated up to the parent to give you that 1 cell, one step up the hierarchy. So I'm sitting trying to get a dead leg. So that's generally speaking the rules as we describe them. We spend a lot of time thinking about this and lots of time on a whiteboard, sort of drawing out ideas. And that's fine. The one thing it doesn't necessarily deal with at the moment is 1 kilometer cells. So what do you do about 1 kilometer cells that are under threshold? So this is something where we haven't agreed a way forward yet, because there's different ways we could do it. We could randomly distribute these small numbers and basically group to somewhere else where they're above threshold. So we could say in the top, in that map, for example, that 4 could be added to 105, and that's above threshold, etc. We could round them up to the minimum. So if the minimum was 50, we could then put them all up to 50, which is not a good way of doing it, but it's definitely a way you could do it. But obviously then everything will be very much overestimating for these areas, especially in rural areas. Or we could group the values, so we could somehow identify maybe a center point and pull everyone into a single point. There might be other ways of doing it, and recently we were speaking to the University of Southampton about this, and they sort of were proposing, they've suggested some ideas that other European countries have done in this space that we could look more into. To be honest, it's not one we've concentrated on at the moment because we deem this to be a relatively simple solution, relatively simple anyway compared to the things I've just been talking about. It's one we've kind of been leaving to last, but it's one thing we're definitely going to need to do something about, because at the moment it's kind of not, it's an unanswered question of how we can get from where we currently are to something that is ready to be used for real data to be ultimately published. So this then leads me on to the grid granulator, which is a very catchy name, and what it actually is our GitHub repository. Again, if you want to scan a QR code, it'll take you to this URL, and you're more than welcome. It's a public repository. You're more than welcome to look at the code and effectively do whatever you want within reason. Well, we can do whatever you want anyway, but you can fork it, whatever. It's there for you to have a look at. I will then say for the next bit I'm going to be talking about, I am not a Python coder. This is all, majority of this was David's work, where David Keir, when he was at ONS. But again, it's the logic is basically implementing the logic as mentioned by everyone I mentioned at the start of this talk. So actually, I can only give you a kind of a high level overview of how it works. If you want more detail, then I'm not the person, but I can definitely take those questions away and get you answers. So it's a Python package using OGC libraries, and I'm reliably informed that it uses the things you would expect a Python script of this nature to be using, GeoPandas, etc. It only actually requires the 1 kilometer and 125 grids predefined to do this, because again, because the coding has that logic, it doesn't actually need the 250 or 500 meters to do this. And again, it's built in this user-defined thresholds, population households into the rules. So the way it's, so obviously coming up with those slides where I was talking about the rule sets and actually then implementing in a code-based way, slightly different to how things have been implemented. To maybe I'm going to quickly just go over how we have done this. So we've effectively broken them into 5 classes of cells. So a class 0 is where nothing happens, it's blank, 0 count, nothing, so you just leave it as it is, unless you have to then aggregate up into the parent cell, which obviously then it becomes, the 0 gets added to the rest to create the aggregation. Class 1 is below the threshold, but small enough to be passed around. So this is again that lower threshold area. Class 2 is just an automatic, but it fails the test. So all the cells, that cell and all its neighboring cells in that parent would have to be aggregated up to their parent. Class 3 is a burrow, so it can take points from neighboring cells to make the minimum threshold. And class 4 is above threshold, so it can lend to neighboring cells. At the end of this process, all cells below 1 kilometer should be either class 0 or class 4. So it's part of a QA check as well to make sure that the outputs we're producing are what we expect them to be. So if we see any 2s, 3s, or 1s, something has gone wrong in the script. These are the rules. These are the number of thresholds we're currently using, but they could, as I said, they can be changed to be whatever they want them, whatever you want them to be. So just to give you an example, again, just of this in practice, again, now I'm going through this, I realize it's quite similar to the previous slide, but this has got a fancy animation, so I couldn't not include it. So this is dissolving up because it's got a class 2. It automatically, even though the class 1 could be moved out the way and shifted to be the class 3 to make it a class 4, because the class 2 is there, it just overwrites everything, and it just means it gets aggregated up to become a class 4 above threshold. So that's a dissolving up. There's also the passing points, where currently there's 2 class 4s, a class 3 and a class 1. The idea that we could just move a class 4 and then move a class 1 record to create a class 0 again. So this is effectively what is happening while the algorithm is running. And to be specific how the algorithm runs, it effectively takes every 1 kilometer cell at a time and then breaks it down to do this. So the actual way the algorithm works, it can literally just take, if you just give it a cell, it'll do that cell and just move on to the next, move on to the next, move on to the next. And that's obviously really good. It's quite simple to do. It doesn't necessarily make it the most optimized in terms of running, which is a point I'll come on to in a second. But that really is as much as I can say about the actual code itself. As I said, it's all out there for you to have a look at and to see and make improvements or whatever you want to do. So in terms of what this does at the moment, this is so the output. So what I showed you before was that map around the Liverpool region was just without any of this complicated shifting cells around. So this is an example then of how an actual output of this script it does. So puts the grid 1 kilometer on, breaks it down. So you've got the 1 kilometer level, which is the overarching. The one thing I haven't mentioned is that we anticipate, I'll come on to a second, but the 1 kilometer level will always be a 1 kilometer version of everything, and then there'll be a 1 kilometer, then the sort of nested grids view afterwards. And then that's a nested grid view where we've clearly got blanks. Obviously, you might be wondering why some of these things don't have cells. Again, this is synthetic data, which I don't think includes every type of place where people live in it. So which is why you've got some blank cells that wouldn't exist in the real world data. This is Bristol, if you are interested in that. So that's the kind of output that script can produce. So that's great, we got that. So now I think the idea that I'm just going to quickly just move on to is just quickly talk about why this could be a good thing for us to have and what the benefits can be. So just looking at comparisons with output areas. Excuse me. So this is an example of output areas on the left and the grids on the right, and this is the Southampton New Forest area region of the country. And as you can clearly see, there are some advantages from the grid-based output. The fact that we can have blank cells is really a good thing here. It means that massive output areas have now been broken up into much smaller grid cells, and having much more realistic population distribution. So you have a better idea of where people are using the grids opposed to the output areas in these more rural areas. But also, if I just zoom in onto the Southampton area as well, it gives you a better potential anyway for a better breakdown of the population, where before, again, output areas, even in inner city areas, can be quite large if they're covering big spaces of green spaces even. So it gives you an alternative way of seeing the population. There are other benefits, which I'll come onto in a later slide, but you can clearly see there is some advantages to the grid-based outputs, just purely on how the population is distributed. And it's a similar story if we just look at the Bristol, North Somerset area. Again, you start to see that maybe this one, the rural areas are not quite as sparse as the one's previous example, but again, it's giving you a different way of viewing the same data in this case and aggregating it, and gives you a better rural picture and a increased resolution within those urban areas, and also breaks apart in this case the more the places of green space and other areas where you don't population are not going to be found. And then just finally, just London again. What it does is what you'd expect, but then big things like Lee Valley and around the River Thames and all the big parks, they then aren't covered. So again, the population is shifted. So things like population densities and things like that you can imagine can be improved using this methodology. Clearly, that's just a very quick high-level summary. If you were to look at these maps in more detail, I'm sure you'll find much more interesting patterns. But I think that is the point of this, that there are more interesting patterns to be seen using this methodology. And that's one of the reasons why we're so wanting to encourage its use and adoption. So just in terms of numbers, so the maps you were showing was maybe we're using as I said, the grid tab. They're actually using a slightly different threshold of 50 rather than 100, which might make it a bit of a cheat, but it's what we think is possible with this. Even if it isn't possible and use the same threshold as output areas, in urban areas the number of entities is roughly the same, but in more rural places you tend to find that the number of entities for using the gridded cells pretty much doubles roughly. Sometimes it's more, sometimes a bit less. So it gives you a greater breakdown of a population, specifically in those more rural places than urban. And if you do get, if we are going down to go 50, then it's definitely creating more cells and more a more granular output, which in my view can only be a good thing. So that's comparing what we currently have with what we could have. But the other thing we are thinking about is, so what are the benefits of this? So why do we do this beyond just thinking of comparing to output areas? So a big one is environmental data. There'll be other use cases, but I'm just going to highlight 3 of them now, and I'm sure I'll be more than happy to hear other use cases where what we're proposing and what we've developed could be useful. So environmental data, so specifically the data that the Met Office 1 kilometre HAD-UK grid has, so rainfall and temperature. So that's a 1 kilometre grid level that is available. And on the left-hand side, we have an output area, quite a rural output area, and then we have a gridded output on it. So the cells, the majority of them are 1 kilometre with a few, with 3 500-metre ones. I think it's relatively apparent from the image that the grid offers a much better way of understanding where the population are. So if you think of that population count, say it's obviously going to be over 100, but you wouldn't know where that 100 really are. You could make some guesses, but the grid obviously offers a better resolution and ability to identify where those populations are. So then when you intersect that with, say, the Met Office data, you can have a better understanding of where the temperature was in that particular cell where the population are. And it gives you that better, again, it increases interoperability and really deals with that kind of large output area in rural areas problem. But in urban areas, we got a slightly different thing. So this on the left is a map from For Earth Intelligence. So they've produced a heat hazard index, which you may have seen reported last summer during the heat wave on the BBC News website, this is the images from on the right. This is where they've effectively taken their 30-meter grid resolution data and the index they've created, and effectively apportioning it to, in this case, I think it's LSOAs, which, you know, is fine because that's obviously at the moment that's a geography where we have population data, we have things like the index of multiple deprivation on, we have lots of data available, but they are quite big, especially in urban areas. As you can see here, this neighborhood that's being mentioned is there's a lot of houses there, and if you were to be able to use, say, and you'd imagine that for the nested grid output, the grids would not be at 1 kilometre, they'd be quite a lot smaller than that. Link that with a 30-meter grid resolution with the actual source data, and then you start to be able to build a much better picture of, say, heat vulnerabilities in urban areas and give a much more detailed picture, because we enable data to be, because we can enable the same sort of data that's currently only disseminated on the OA, LSOA, MSOA level. If we can get it on a grid like we're proposing, you've got a much better way then of interlinking, potentially dealing with large, mid-sized geographies in urban areas. And then just my last example is pollution along roads. So nitrogen dioxide emissions are on a 20-meter grid here. This is in central London, and you can clearly see it's following roads, which is not surprising, but also it's a lot of pollution. The half-life from terms of how far they travel from roads is, not everything is the same, but roads are typically quite a big contributor to pollution. I'm sure people who know more about the subject can correct me if I'm wrong on that, but generally speaking, roads are important when it comes to things of this nature, because that's where quite a lot of the pollutants come from. If you then look at an output area geography and overlay it onto a map, you'll see that quite a lot of center lines are along roads. That's because they're designed that way. So if you can imagine, if you've got pollution data along a major artery of a road artery, and your output areas all use that road as a center line, it means your population is either side of that. In theory, they're both equally impacted, but the population effectively is diluted because the output area could be going quite a few rows of terraced houses, streets back, and obviously the impacts of that pollution that far back could be a lot smaller, hopefully, than the ones nearer to where the actual sources are. A grid doesn't deal with it perfectly, because obviously a grid is still dealing with the fact that it's still got straight lines, but it's more likely to be a useful thing because, one, it's gridded, so it links with a gridded data anyway, so it's better for, like, the 20-meter fits into this. Well, it doesn't fit perfectly, obviously, but it does have the ability to do so. But also, it doesn't use road center lines as a problem. So your population is, you're more likely to capture the population either side of the road within a single cell than you will do with an output area. Not obviously guaranteed, but that's the kind of thinking we've had. These are kind of examples that we were thinking of when we were kind of proposing why we should be doing this in the first place. As I've mentioned, it's not a completed project yet, still a work in progress. So these are things problems we're currently thinking about, working out what to do. I think should be, well, hopefully it's obvious that if we're producing a geography around a data, every time the data changes, the grid will change. That could be a problem, or it might not be a problem, depending on what you want to use it for. So as I said, the 1 kilometer level could be that interoperable level where everything gets aggregated up to what you're having available at the 1 kilometer level, and that's the same geography then for every, say, univariate statistic you want to do it for. Or one way we might want to consider is what other countries have looked into doing, which is, rather than having counts, we do proportions. So you basically have a base cell on the base population, and then you use a proportion within that cell of a certain thing, but certain category, whatever it might be, belonging to that cell. Again, these are some ideas we have not really thought about. We've been very much focused on getting the grid itself working properly, which we're not quite there yet, and then worrying about the actual how we will disseminate using this problem. But we're fast approaching that point, so we're something we're going to have to consider in the very near future. One of the other issues we have is grid cell assignment. So an issue that we have at the moment is that the code can't handle the whole country. It needs to be chunked by local authorities. And as I previously mentioned, it does it by 1 kilometer level. So this green cell is a 1 kilometer cell broken down into mostly 125 meter cells. This red line is interesting. That is the border between England and Wales. And if we were going to say, and this is in Chester, if we were going to chunk that 1 kilometer up by its local authority, it will belong on the English side, which means even though it breaks down to very small levels, all those cells potentially would be English 125 meter cells, even though they are very firmly in Wales. Now, does that matter? It goes back to one of my first points about being used for analysis. Maybe, maybe not. But it's one of the things we need to consider. So one of the things we are looking at is trying to improve the code so it can actually improve the efficiency, so it can run for the whole country at one go. So we don't need to chunk up places like this and then have consistent assignment of cells from the 1 kilometer level down to the 125. We can do it a different way and do it so that it can go from the assignment from the bottom up, so that then whatever cell it intersects with, that we can then do it's assigned to the right geography or the close approximation. It'll never be perfect, but we can probably do better than what we currently have. And different totals. So this goes back to this point about, does it really matter for analysis? So if we were to do a nested grid output for an area and then sum the total and then compare that to the actual number that's been produced for, say, a local authority, it's very likely those numbers will differ, not by a lot, but by some amount, just because of the way that the cells, again, intersect boundaries in funny, jaunty angle ways. Does this matter? Maybe. It's something we're thinking about. We can implement stuff there are ways we can implement it so we can effectively bring people who are outside of a boundary back in, or vice versa. Again, it depends how we solve the previous problem, how we do this. However, if you're thinking from an analysis perspective, if you're thinking like the environmental data, does it really matter if your count for a local authority is slightly off compared to, say, the true number? It's one we will be interested to hear people's thoughts on, because it's one where we could develop a solution to this, or it might not be necessary. And I'm very quickly running out of time, so I'm going to have one last slide, just my final thoughts. And just basically to reiterate what we've done. So we've created a methodology to produce flexible geographies around data. And I think that's the key thing at the moment. How far we got, we've definitely done that. It can be fine-tuned without question, but we definitely have come a long way since when we started this project. My view is this kind of output allows for increased interoperability between data types. It gives a better, and it gives you more opportunities to basically use the type of data that ONS could be disseminating using this geography better, effectively, gives you better accuracy of where the populations are, things of that nature. And that ultimately increases the usefulness and use of data, which can only be a good thing. So I will leave it there. Just say thank you very much. That was very much a whistle-stop tour of kind of our thought process and what we've done. I can see some questions in the chat, but I'll stop there for now and just say thank you.
Thank you very much, Chris. I think that was an absolutely fantastic talk. I see some people clapping, and I think this is the sort of like the downside of doing a web talk, is that you can't hear people clapping at the very end. But thank you so much. So people are welcome to stay around longer than 5 o'clock, as long as Chris can. I don't want to keep Chris here longer than he has to, but there are a couple of questions in the chat. So we'll go through the chat one by one, just in case, going by order. So the first question, and I'm gonna say just at the beginning, sorry if I mispronounce your name. My pronunciation is what it is in English. But I will start with Joe, and they ask about, in terms of when it comes to jaunty angles, why not using hexagonal grids, which I would guess it maybe triangular might be more feasible, but the question is about hexagonal grid. I don't know whether Chris has any view on that.
So we did look at other types of grids. So I saw that Isam's on the call as well. So when he was at ONS, he was doing stuff on discrete global grid systems, and which obviously use hexagons. Hexagons are the bestigons, obviously everyone knows that, but they are not necessarily the bestigons for the UK, predominantly because we have Ordnance Survey as a world-class mapping agency who do things in the British National Grid. We have a close working relationship with them, and the data they supply that could be used of this as well, it comes in that kind of more square-based view of the world. Basically, we didn't want to basically rock the boat too much and use something else. There are clearly benefits to using other types of geography, especially ones that have more sides on them, for terms of interactions between spaces, and it's something we might want to consider in the future. You could see this as potentially the first step in a journey for ONS into this kind of more flexible geography building type space, and it depends kind of where our priorities lie. If it's just the UK, it makes sense to stick to the British National Grid because it's a well-established way of looking at the world in this country. If we want to go further afield, then there may be a different type of grid-based system, but also the things with nesting element of it, obviously different shapes have their own challenges as well, and a square is quite relatively straightforward to do. So that's a very short version of why we kind of stuck with what we basically knew the most of, which was that kind of square-based grid.
Fantastic, thank you so much. I then have basically two, I think, kind of related questions, one from Chris and another from Liam. So Chris asked why not to make the code reference match with basically the military grid reference system. And then Liam asks whether you're aware or whether that could work also with C-square, which is another global hierarchical grid based on WGS84. Again, in marine MAPI, I don't know whether you have had the chance to look into those and how these relate to the British National Grid.
We haven't looked at them is the quick answer, but it's not to say that we wouldn't do that. It's just, again, we were sticking to things we knew. The thing I didn't mention about this, because again, I could probably talk for longer and waffle more about this topic, is that the way this project first started was working with Ordnance Survey. So obviously when you work with Ordnance Survey, they have they're more likely to be sort of directed towards certain ways of doing things, certain grid systems. And I think we just, as that project kind of sort of had to end because of various reasons, and we kind of took it on ourselves fully. It was just a legacy of that we weren't really going to change at that point, just because we'd spent quite a lot of time thinking about the problems and issues that I've sort of mentioned during this talk. But again, nothing's off the table in terms of future development when we haven't used this to publish anything yet, and it doesn't, just because we use it once, again, it could be a suite of grid-based systems. I don't know, who knows. But yeah, and they're all good ideas. It's just nothing we've looked at for this particular work thus far.
Fantastic. Thank you so much. There is another question from Chris, but I think I will jump to another one from John. So I give people a little bit of sort of like equal opportunity to ask questions. So the question from John says, for continuity on record swapping, is each 1 kilometer square an individual unit, or could a 125 meter cell from the east end of one kilometer block borrow from a 125 meter cell from the west end of? So I think this is a similar question that I was thinking about. So can cell borrow from the neighbors, I think is the short version.
It takes the 1 kilometer, and it's constrained to the 1 kilometer. So even if there's a cell just the other side of that 1 kilometer that it could borrow or take from, it won't do it. Again, it's the programmatic way of trying to address this. We weren't trying to be, clearly there's other ways we could try to deal with this issue, but we felt that keeping to the 1 kilometer, because what could happen in theory is you could then daisy chain them along, and in theory you could then ultimately move a record quite a long way away from where they started off. At the moment, it's perfectly feasible that a record in the bottom right hand corner could get to top left hand corner by the time the process is finished. But you've only just gone from one side to the other side of 1k square. If you start allowing beyond that 1k to be swapped in, then they could also make they could be quite a nomadic journey across England or Wales.
It will be quite interesting to trace that back.
Wow.
We have another question, and question keep coming up. I can see the chat very active. So there is a question from Sarchil. I assume that's pronunciation. If that's not the pronunciation, again, apologies. Well, thanks for the presentation. It says, having a grid output is quite handy for many spatial analysis in different applications. One limitation of the grid output with sensible boundary is that the derived grid outline might not align with the landmarks such as roads, which I think is what you were mentioning, buildings, and are needed by numerous ground during the survey. So it says using grid output might require calculation of some complex adaptive sample probability weights or risk incorrect weights and estimate. Not sure about the efficiency of the method that you have used. We have done similar work, and then there is a link to a quad tree algorithm. So I guess the question is how that has an impact with working with, again, landmarks in particular.
Well, it's one of those things where it's kind of, we've almost not, it might sound counterintuitive, but we almost don't consider the real world at this, in terms of how we've been dealing with this. We've very much been concentrating, as I kind of alluded to, that on the record swapping element of it to try and get that bit right, because that's fundamentally for ONS to publish anything using this method, that's the bit we have to get right, because that's the bit that is potentially problematic if we get it wrong. Then in terms of how, obviously, what the grid we use and the way things nest, the way things move, these are all they're not up for debate as such, but we can change them at some point. That's the thing. So in terms of like real landmarks, it's not a thing we've considered. We've just basically gone with, this is the grid we've used. Where it falls is where it falls, and then depending on where things, the more of the issue is things like where your record literally fall on the line, so they end up and like having to basically move them across to make sure they don't go into multiple cells. Things like that are the more practical things we've had to deal with, rather than the real physical world and any of the consequences of doing that. Again, we can make this more complicated. I'm all for it. It's not we haven't, it's just we're a small team. Like the people I mentioned at the start, that they've not all been working at the same time. People have come and gone, so we haven't had time to and chance to really think about the wider the wider issues that might be around what we're proposing here. But this is why I'm interested in these comments, because I would like to know more, and I'd like to sort of engage with people who are interested to try and understand more. Also, the fact that I appreciate people on this on here come from different backgrounds, different to mine. They know stuff that I don't know, and I'd like to be educated as well. So yeah, more than happy to speak to people outside this again about specific details about what I've talked about, which is a very long-winded way of saying we haven't really considered doing that stuff at the moment.
Fantastic. Thank you so much. There is then, well, Peter asked whether he can advertise GISRUC 2023 in Glasgow. Yes, please do. If you don't know about GISRUC, please have a look at the link posted by Peter. Is a GIScience conference which is happening in Glasgow this year and happens every year here in the UK. And
I'm also
there.
Yeah, I will be there, and I'll be talking for 12 minutes about this. So if you do go to that and come to this talk, I promise to put some different pictures in.
Yeah, fantastic. You can think more about this presentation and get some very, very difficult questions to ask Chris there.
Oh yeah, well, I can't squirm away. You can corner me.
We then have a question from Caroline. So the question is asking whether you're going to produce data at this level, and or whether the shapes are going to be available to manipulate their own data on this grid. I guess the answer is obviously everybody can use the grid manipulator, but it would be interesting to know about the sort of production of data at this level. What are the plans? So
the data production plans is that we had some discussions a while ago with our colleagues in Census. And there is interest in this in terms of if you were to read the Census outputs consultations, you'll see there have been questions about grids, and we have had, I think the response rates were 50% were in favor, 50% were not. I always say that 50% who are not don't understand the benefits of grids, so they are the 50% that need to be convinced via things like this to talk about it. So we've got some commitments to doing it. It's at the moment they're very busy with the stuff that we've been released this week. Some more traditional ways that we've disseminated data, and also new ways of actually accessing it via the way you customize your own data. The plan would be at the moment would be to basically pre-can some univariate statistics using this technique. It won't be everything; it'll be some things, and then I guess one of my penultimate slides was talking about how we might go about actually disseminating that. What is it? Counts, proportions, those kind of things. It's not going to be something that's going to happen in the near future. It'll be towards the end of the year, maybe next year. It really just depends. There's a lot of things going on that need to happen in a certain way. And as I say, because we haven't been able to spend a lot of time, focus time improving this, we have got some issues we need to kind of address before we can kind of have those discussions and sort of re-kick in get some really solid plans on how we want to do this. But we definitely want to. But obviously, if you have access to record level data, I've shown you my newbie level questions on Stack Overflow, and the answers there let you build a grid just like we've done, exactly the same. It's all there, and you've got the data, and you've got the grid granulator, and you've got the bread. I can also show you where the basic R script that does the stuff about this record swapping to give you a starting, really like 20 lines of code. It's all there. You could do it yourself and do your own outputs, and it'll be aligned to what ONS are planning on doing. As I said, some things like the coding for the actual cells might be slightly different at the front, but that doesn't really matter for this. So we got a plan. We just haven't got anything confirmed. But obviously, all the bits are available online for you to go away and do your own things using these techniques.
Fantastic. Thank you so much. Do you have time for another couple of questions?
Yeah, it's fine.
Okay. I think there is a seemingly quite popular point from Paul, who says that why are the final 3 digits of the identifier in the order 125, 250, and 500 rather than 500, 250, 125? So the latter would be sort of like what would expect, so from the bigger to the smaller.
Right. It's so you can basically knock off the last digit, if you see, because if you know that your third character is always 0, you always know that that's not a 125 meter grid cell. Whereas if it's the other way around, you could still do it obviously, but it's easier just doing it that way. It's what we came up with as the optimized way of basically cutting out a step of coding, which is why the grid granulator stuff doesn't need the bits in between, because it can work it out from the 125 meter code. There's a logic in it, basically.
Yeah. And also, I'm going to ask a question myself now. Why is it in counterclockwise order, like the 1, 1, 2, 3, 4, rather than 1, 2, 3, 4 the other way around?
I think we matched how Ordnance Survey do it, because if you look at an ordnance, if you look at that, right. The slide where I had how there's on the Stack Overflow question as well. The way that OS do it, it's not the way you think you'd be doing things. It's not like left to right. It's kind of it's a different way. And I think we replicated that. I think it's like a backwards Z.
Right. Oh, yeah.
Right. I think there's a reason why. I can't remember the topic. That was a 2019 discussion. So that's pushing my memory back. But I think that's why.
Cool. Fantastic. I have 3 I think quick questions. So one is whether the pipeline would be feasible in R or whether it's too computationally expensive. I guess would be if it can be implemented in Python, maybe R is a bit slower, but not massively.
I think the general principle is that if you're doing it one, it'll just chug through it. If you can come through, I'd love to see an R solution, because that's something I would actually understand. But it's not one kind of the person we had doing it was Python, so they did it in Python because they were expert in. If they had been an R person, I'm sure an expert in R, they could have done the same thing in R. It might have been a bit slower, but speed is not necessarily it's not so much the speed, it's more the being able to finish, which is the issue we have at the moment. It kind of just hangs if we do it, which might be a limitation of our hardware. We don't really know, but obviously it's one of the things it's one of our priorities moving forward is to basically be able to produce the whole of, well, England and Wales at least, using this technique.
The problem is that it starts swapping records around and can't find a good solution.
Well, we don't know. We didn't really have enough time to kind of, before this person left, to kind of dig into it in more detail. It was interesting. Sometimes like things just get slower as they progress. It's like, and again, it could very well just be the hardware that we have, which isn't the best, could be a contributing factor to that. But it's one of the things that we're looking to explore. We're actually getting some help from the University of Southampton on this, and hopefully next month we might make some progress on it and be able to do it. But that, I think, unlocking that solves quite a few, or at least allows us to sort of deal with some of the other issues I've highlighted.
Fantastic. And I think this is the last question, and the last one is just a thank. So the question is, how difficult would that be to adapt the Python model for a similar grade in Bangladesh compared to the UK? So is it quite flexible as a Python code, or has some of the national office OS grade like ingrained in the code somehow?
Well, the code is pointing towards things that might be only internal, but it's only because where we like store like boundaries and things like that. In theory, it could work in anything. It's like if you've got a grid system that's like that, then yeah, it would be fine. It would work with any kind of cell-based, effectively, you replicate what we've done just in a different place of the world, it'll work.
Fantastic. All right, I would have a lot of questions, but it's 10 minutes past the hour, so I'll let Chris go. Thank you very, very much again. It's been absolutely fantastic, and thank you to the 40 people that have stayed with us to the very end. We had, I think, up to 80 people on the line. So I think it was very, very good. Quite popular, I would say. And yeah, thank you very much again, Chris.
Thank you, everyone.